Many of you know Valor as a design for manufacturing validation tool used by your fabricator and assembly house vendors, and recognize the reports sent back to you highlighting issues with the manufacturability of your designs. In this webinar, we will review the value of using Valor NPI earlier during the design process. We will begin with the NPI business process and review and release process today. We will show how Valor NPI can complement the layout DRC checks and describe what we mean by manufacturing-driven DFM. We will conclude by demonstrating how the review and release process can be improved with Valor NPI. Let's get started. The new product introduction process spans both the design and manufacture of printed circuit boards and requires a clear and complete communication between the two. Mentor's Valor NPI application software helps you accelerate your new product introductions by recognizing the manufacturing impact of PCB design, optimizing the design for volume production, and communicating complete PCB design data to manufacturing. There are multiple steps in the new product introduction business process. The first questions are, does it work? Can it be manufactured? And how? During ramp to volume, it's what can be done to improve yield. Alternate parts, for example, alternate build locations. For volume through end of life, it's lowering the cost of production and improving product reliability. Using prototyping and production to find DFM issues is time-consuming and expensive. A rule of thumb for design is that it costs 10 times more to fix a problem with each step, and the most expensive failures are the ones that you find in the field. I think Boeing would agree with that. So DFM shift left reduces the time and expense of fixing DFM issues and optimizes NPI success. Very often today, the DFM checks are being done by the fabrication supplier and assembly supplier at the time of release. This is too late in the design process to allow changes to be easily made. Or a manual review of the design is done at the end of the design cycle. This is still too late and results in either a delay in the release or a decision to defer changes to the next revision. Valor NPI complements the design rule checking you are already doing during the design cycle, adding checks that can impact the manufacturability of the PCB. Many of your suppliers are already using Valor to check your design when they receive it. You can check the designs earlier using rules aligned with your supplier's capabilities and aligned with their manufacturing processes. Different manufacturing processes may require more specific checks than those found in traditional DRC. For example, DRC may check for a minimum annular ring, but DFM will check the annular ring based on the manufacturing process, laser drilled, mechanically drilled, or back drill configurations, for example. DRC has a drill to copper spacing rule, but DFM will analyze the drill to copper spacing based on the manufacturing process, plated through versus non-plated through holes, for example. The MRA is our main tool to facilitate the review of any number of analysis results, and it does so by grouping them into assessment areas. Each area relates to a specific fabrication or manufacturing problem or process. A summary pane provides an overview of results of all assessment areas and categories. The MRA can be used to sort and review analysis results, isolate issues that will most affect quality and yield, define groups and run analysis actions, and report issues of interest. The Valor Parts Library provides standardized information about the components that will be mounted on the board, based on the manufacturer and manufacturer part number in the bill of materials, or ABL. The standard boundary definition and height property allow a wide variety of checks beyond standard DRC rules. The pin information allows a virtual build of the board to be performed, identifying pin-to-pad issues that can affect the quality of solder joints. Solder validation requires comparing the CAD footprint in the design to the pin contact area of the pin from the Valor Parts Library, allowing the checking that the solder DFM rules are met and validated measurements such as toe, heel, or side solder requirements for rectangular pads, and periphery requirements for ball pins. The MRA revolution was first introduced in the Valor NPI 10.0 release and has been expanded into assembly analysis with the current 11.0 release. This has allowed Valor to pioneer the concept of automated manufacturing process-driven DFM. The MRA revolution is a new approach to DFM rule creation. It greatly simplifies the process, making accurate DFM results much easier to achieve. It makes use of PCB design technology and process constraints to automatically determine the DFM analysis to run, as well as the DFM rule values to utilize. It provides a more streamlined DFM process and eliminates the need for legacy ERFs and checklists, and makes current DFM, needed for the left shift methodology we discussed, more practical. The MRA revolution can be set up to understand the stage of the design and perform only the analysis needed at that stage of the process. Manufacturing process-driven DFM is as easy as 1, 2, and 3. To properly assign the appropriate constraints rules to the design, we have the ability to set up various design factors to help make these assignments based on attributes within the design. In this example, we have added factors such as drill size, copper weight, layer count, typical trace-to-trace spacing, as well as typical trace width. The next step is to define classification sets, setting up this product model-centered approach to DFM that we call the MRA revolution. The system will interrogate the design for these factors, and for any classification that fully passes, the system will assign the constraint values. There can be many different classifications, such as technology types, design stages, or even possibly vendors. Then the third step is to update your constraints for both the classifications and the factors in the constraint area, so you can easily fine-tune exactly how you want to set up your rules to analyze your design. For example, we can select factors such as copper weights of 1/2 ounce, 1 ounce, or 2 ounce, along with layer size for inner and outer layers. Now we can select each of the constraint categories and set up constraint values for these factors. Here is an example of manufacturing process-driven DFM. Based on the factors in the design, Valor can determine if the design contains any micro-vias based on the standard IPC definition. If the aspect ratio is less than or equal to 1.0 and the depth is less than or equal to 9.84 mils, then micro-via analysis is automatically performed. If there are micro-vias and at least one layer designated as a build-up layer, then HDI DFM analysis will be executed automatically. Valor NPI is the only DFM software that is manufacturing process-driven, using the knowledge of which manufacturing processes apply to automatically determine the correct checks to run and DFM rules to use. When the design is ready to Valor, the design factors drive the design classifications, which then drives the manufacturing constraints. All this is based on the software knowing the manufacturing processes applicable based on the design. Running design for manufacturing checks during the design process supports the shift-left methodology we discussed earlier. Finding DFM problems earlier in PCB design saves time, as fixes can be more difficult at a later stage. Running incremental DFM analysis means that the issues are identified directly to the engineer responsible for that stage of the design and release process. Another interesting effect is that it helps PCB designers become more aware of design choices that affect the manufacturability of a PCB. Running Valor NPI even before placement can identify library issues, such as incorrect pin-to-pad size or pad alignment. It can also identify graphic silkscreen or improperly defined gang masks for fine-pitched devices. Valor checks after placement can identify problems such as component clearance violations based on the standard component definition from the Valor parts library. components too close to a conveyed edge, or even tall components too close to adjacent components, making it difficult to access the short component for repair. As someone once pointed out to me, changing component placement after routing can be difficult. It's like the components are mounted in cement. Running the DFM checks during routing can identify common fabrication issues, such as slivers that can cause repeat defects due to photoresist flaking, star thermals, and circuits too close to the mask clearance or on a pad that can result in solder bridging during the assembly process. Flexed and rigid flex circuits have their own manufacturing requirements. Conductors need to be perpendicular across the entire bend area. Plated holes need to be a sufficient distance from a stiffener, and rigid areas of copper too close to interface areas can cause copper to crack, and silver masks must remain clear of exposed copper to avoid EMI issues. Validation of the manufacturing BOM assures that there are no ref desert quantity mismatches. The pin area component data from the Valor Parts Library allows the virtual mounting of the components on the board, identifying solder issues that can lead to weak solder joints, such as insufficient heel or toe distance. Even the ratio of heel to toe can affect the quality of a solder joint. The component outline data can identify other issues. For example, shown here is a case where the actual component body, shown in red, covers a mounting hole that the CAD package outline, shown in purple, didn't detect. At this stage, alternate parts listed in the BOM can also be analyzed. In this example, components A, B, and C are listed as alternates in the bill of materials. Components may have the same electrical properties, but slightly different body dimensions and pin contact areas. To confirm that no matter which qualified parts are actually sourced, there will be no manufacturing issues, each of the qualified parts are compared to the footprint in the design. Valor simulates the mounting of component A on the board. In this case, a toe violation is identified. Component B is validated, and for component C, there is a pin to pad side violation. The final review brings all elements together. If the DFM checks are not run until this stage, you can be spending time fixing issues that would have been identified earlier, delaying the release of the board. A few additional examples are shown here, such as different trace widths connecting pads that can cause the component to tombstone during reflow. Traces under a zero offset device may cause the component to rock, resulting in a poor solder joint. Adjacent layer copper may make it difficult for SMT equipment to identify local fiducials, or too many test points within an area can stress the PCB, potentially affecting the solder joints in that area. If the checks are being performed during the design cycle and manufacturer's issues addressed as they are found, then when the design is released to manufacturing, there may be no more issues and the board can then be built. I hope we have been able to show how using Valor NPI for an efficient and effective design review process can result in lower PCB costs, improved PCB reliability, and a streamlined release process. In an Aberdeen Group survey, they found that companies using Valor DFM averaged 1.2 revision spins per design, a 57% reduction, resulting in a significant savings in material costs. Let's move on to a demonstration of a typical Valor NPI analysis. So what I've here is I've invoked Valor NPI, as you can see from the window, and I'm in the main window, which is called the Engineering Toolkit. I have the ability to set up design centers, and so I've created a design center specifically for this webinar called Webinar. Design centers allow you to have either checks for different vendors or checks for different processes or types of boards that you might build. So in this particular mode, I'm going to run what's called a design process wizard. Now this wizard will go and let me load in a configuration, and I'm going to load the configuration that was created within the webinar design Design Center. I open it up. You can see here, these are all the steps that are going to be automatically executed for this particular check of this design. I'm going to turn off the final checks at the end. It turns out that for this particular board, although it's a complex board, it takes only about 4 minutes to run the Valor checks on the board. But 4 minutes, although it's a short time for someone to wait for results, is a long time to run in a demo, in a demonstration or webinar. So I'm just going to stop at that point. I'm just going to start this up and I'll show you what I do. I pick a data location. So what I'm doing now is I'm importing the data that I'm going to be used for the design. This happens to be in an ODB++ format, and this is the standard way the data is transferred from the layout tools. This allows us to be compatible with a range of different layout tools, not only, of course, pads and Expedition from Mentor Graphics, but also other tools like Allegro or Altium or Zuken, because they all can export an ODB++ file format. So this is what I'm importing into the location. I'm also going to import a bill of materials for this particular design. Like that. Okay. So then I go on to the next step. Okay. I'm going to create an input source, and I'm going to create a file, and I'm going to call this just input demo. And it's stored at this particular location. Now, I'm going through and I'm doing the standard import of data into Valor. I'm going to choose to run the MRI Revolution classification set called Master Sample VPL. You see at this point I could choose which one that I might want to run. I'm also going to select the stage to run. Remember I talked about being able to run checks at different stages, and so the MRI Revolution can be programmed to do different checks or look for different factors at different particular stages you happen to be running. I'm going to run a one called demo. I'm also going to set the IPC level. Because we have the pin information available from the Valor parts library, we can simulate the mounting of the pins of the component on the board itself. Built into Valor are the standard rules for pin-to-pad clearances for A, B, and C class IPC boards. So I can choose which level that I want to run this at. If I were running a standard Valor, I might also run checklists to run bare board fabrication, or I might run checklists to run assembly analysis. Okay, in this particular case, I'm not going to do either one of those because I'm going to be stressing the use of the MRI Revolution. Okay. I am going to run a preparation rule set on the design. What this commonly does is it adds properties to the design so that it can sort of enhance the checks that are being run. So for example, it may identify 0402 or 0201 components, which might have different mounting strategies. It could identify fiducials on the board and identify other aspects of the board that will help in the checking of the design. Okay, I mentioned the fact that I'm going to be processing the bill of materials, and that's so that I can make use of the VPL. Okay, the system is coming and checking. It's the layer stack up with this particular board, of course, is going to come in correct because I'm importing it from an ODB++ data source. And the same is going to be true of information about the tooling holes that might be. This is the board outline check, and this is the tooling hole check. Or not tooling holes, can be drill checks. So now what it's going to do is it's going to go in and it's going to analyze the bill of materials that we have. As you can see here, it automatically read a format, found a format called Aspen Demo that reads this particular formatted bill of materials. There's a lot of flexibility in how this can be programmed to read in different file formats that you might generate your bill of materials in. Notice, by the way, there are 2 errors. Let me go see what those errors are. If I scroll down through my list, everything looks fine until I get to this point right here. That's the error. If I scroll over to look what the data is doing over to the right-hand side here, what you'll see is that although the manufacturer for this particular part was identified, there was no manufacturer part number identified. And so we're not able to look that part up in the Valor parts library for that reason. If I continue on, the system is going to now interrogate the Valor parts library and determine whether it can find matches for the components. You'll see here that it's found matches. In some cases, it found matches by the CAD package. In some cases, it found what's called an extended search, which meant that the part number was very close to a part number that was in the system. And notice that for CAD package and extended search, I have the possibility of rejecting those if I wanted to. In these cases here, these were exact matches. The part number exactly matched the Valor parts library, and so those parts are correct. Okay, so the Valor parts library matches has happened, and now I can continue on from there. So what it's done is it's read the information into the bill of materials that I'm working with in the design, and then it'll validate that and continue on from there. So what this has done is it's created a bill of materials that has the mapping to the Valor parts library included in it. So now the next step in the design would be to sort of incorporate that into the design itself. So what we've done is what's called an assembly merge, where we've taken that bill of material and VPL information and added it to the design itself. So if I go and you can see I have a report here about the VPL merge. And it identified cases where I have set this up to automatically mount the component the best it can on the board. Okay, the placement review is saying it ran into some issues doing that, and maybe you should review this possibility. So if I go like this and look, you'll see that if I scroll in, it might be hard for you to see, but the pin location is superimposed on the pad location. So it has correctly mounted this part onto the board, but it's showing me that the way that the component was identified in the database had a different origin to it. And so although it mounted it correctly for you, it's just warning you that that was true. If I go on and look again, you'll see that it mounted this component, but it had some problems with the pin up here. It seems like the corner pins, both on the top and the bottom, don't quite line up with the pads. This could indicate that there's a problem with the footprint that was defined in this particular design. This is an example of a check that would have been done in the first or second stage, either possibly just with the placement of the design. So this problem could have been fixed early on in the design process. I'm going to go on from here and continue. So now it's gone ahead and it's now identifying for the components in the board a package type and a lead form. Much of this information comes from the Valor parts library, and so you can see that most of them are filled in. If it was necessary, I could identify that maybe this particular component, which did not have a package type defined, I could then look at it and manually define that for the design. Okay, when I manually define this for the design, that can be saved away. And so then in the future, BGA96_DD3_SD-RAM package name will automatically be identified as that package type, even if it was not found in the VPL. I continue on from that process, and what it's going to do is it's going to read the design in. It's already merged the data, and then next step it's going to do is to run a data preparation step. Okay, so because I stopped it before it went to that particular phase, okay, the Jane processor wizard had stopped. If I continued on from that point, it would have run the check, which I said takes about 4 minutes on this design, and then would have displayed the results in the MRA. What I'm going to do is I'm going to go and manually go into the MRA. with the copy of the design that I processed earlier. And then we can look at the results that were stored in the design. Now remember that all of these checks were run automatically based on the factors in this particular design. I didn't have to decide which checklist to run or which rules to apply to those checklists. Okay, it's divided up into etch, solder, mechanical component placement errors, etc. So if I go and I look at my etch errors, you'll see that my master sample VPL ran the classification set called complex 4x4 mill. Let me go in and go into it as an administrator and look at what that means in the design. Okay, that's opened up some extra windows here. The system is designed for users to be able to easily process it. An administrator level allows me to go in and edit factors and classification sets and things like that. So for the master sample VTL, which is the one I'm running right here, here are the factors that I've been able to look at in the design to determine which category classification I want to run on this design. Each one of these classifications has different rules associated with them. If I run a test, what you'll see is that the complex 4x4 mill was the first one that passed all the different factors. And so that's why complex 4x4 was the design that was being used. Okay, for that particular design, these are the constraints that are being set up. I can customize the factors that I might use in this design, and I can customize package types that are defined for this, or soldering requirements, etc. So here you can see here the soldering requirements that were built into the system for IPC levels A, level B, and level C. Okay, so let's take a look at what's happening. Signal layer checks, complex. These are the checks, these are usually fabrication checks. If I go look at CAD short, what you'll see is the system has identified the case where two different nets have been shorted together. If I display the feature, I can look at the net associated with this particular line, and I can look at the net associated with this one, and you can see that they're different. Via annular ring. This is interesting. This has identified a case where I have a via annular ring of 2 mils in the design. Okay. The rule says 3.44 and 4.6. That means that any annular ring less than 4 mils will be reported as yellow. Any annular ring less than 3.4 will be reported as red. This was measured at 2 mils, so it was reported as a red error. Interesting, this is the only one in it. The 8 that you see here happened to be that same via on the 8 levels of the design. So interestingly, this is an artifact that's left over, because if I actually queried its features on the design, you would see that it has no net assigned to it. Okay, same is true here. The stubs. There actually was a stub in this design, which is a piece of copper that was added somehow, but isn't connected to any net or anything like that. So these are the kind of errors that you can find early on in the design process that you're working with. Okay, I go down and I look, instead of etch errors, I'm going to look at solder. So now we're looking at solder issues. So for example, there's mask issues with the design. And down here you can see I have 12 cases where there was a solder bridge of 4 mils, and I have one case where it was 0.8. If I look at that one, you'll see it's that same stupid via that somehow got accidentally added to the design. So when that deletes, I'm going to have other ones. The ones that are 4 mils are just cases where this particular case there happens to be a mask, gang mask on this, which exposes it to the adjacent pin. Okay. Of interest, though, is if I go down the solder validation checks. These are the checks that have been run automatically based on the fact that I chose IPC Class C. So you can see here, this is the R-convex check for toe check using classification C. If I look at that particular case, you'll see it's that same component that I was identified as a problem early on in the design process. So I could go and I could review other cases where there happens to be toe or heel or other or side-to-side issues which might affect the quality of the solder joints. Okay, I think that's given you a quick idea of how Valor works in the design process. And thank you all for attending this webinar.